for inviting me and giving an opportunity to give this tutorial overview of a very interesting and emerging topic at the intersection of data science and systems or dynamical systems. And we did mention briefly dynamical system. So it goes one step above the standard modeling that one normally gets into. I'll just turn off the video to save on the bandwidth. Right. So this goes one step above the standard modeling that you see in data science. So the partitioning of variables has already been done for you. Whereas in causal discovery, the challenge is to figure out which variable belongs to the input space or the cause space and which variable belongs to the effect space. And very interestingly, the variable can belong to both spaces. So that is a lot more interesting. The objective of this talk is to give you a tutorial overview of not only the developments in this field, but also obviously because this is a tutorial talk, I'll spend some time on the basic concepts associated with causality, especially in dynamical systems. There is a lot of causality analysis done in static systems or probabilistic systems where there is no dynamics and so on. But this talk will focus I move on to give you an overview of the causal discovery there. Again, I don't claim this to be very exhaustive. The literature is growing at a very rapid pace that sometimes it becomes difficult to catch up with. A bulk of this talk will focus on two very popular, in fact, one being much more popular than the other, at least preceding by about 50 years of Granger causality, than the convergent cross mapping, which is about 10 years old. There are a few other methods, of course, for detecting causality, but I chose these two for a few reasons that I'll make clear later in the talk. And then with regards to handling either of this, how do you handle certain special cases, especially when you're using Granger causality-based methods? And I don't say that the case studies will be presented separately. What I mean by embedded case studies is as and when we unravel a concept, I would present a case study to get clearer insights into the implementation. So we'll obviously keep it at an illustrative level. The software that is used for implementing these methods varies. You can use MATLAB, you can use Python, and so on. I'm not going to show you any demos today, but if you are interested, you can always write to me and I can help you implement or give you directions implementing these methods. There are, of course, other sources on in the literature as well. So let's move on and ask ourselves, why do we want to actually look at cause-effect relationships and what is it that kind of attracts our attention there? For those of you who are familiar with modeling dynamical systems, who have taken courses in linear systems theory or even nonlinear dynamical systems and so on, you know that the classical systems theory representation assumes that a process is excited by a few inputs here, and then perhaps subject to disturbances. By the very definition, disturbances are beyond the user's control. And then it responds, which we call as output. So this has been the backbone of a lot of developments that you see in systems theory, systems engineering. However, in the last at least a decade or more, in bits and pieces, but mostly paradigm shift in the way we mathematically represent the process. And especially that caters to a lot more situations than the classical systems theory can do for you. And this has got to do with the network representation. And the understanding here is that the nodes, of course, networks come in different shapes, sizes, flavors, and so on. And what the nodes and edges represent can vary across domains. If you turn to standard graph theory, nodes will represent some kind of a linear algebraic operation, whereas edges would determine flows. For example, flow graphs are very popular. On the other hand, if you turn to standard network science that is used in time series modeling, analysis, and so on, you would see variables sitting at the nodes and the edges determining the propagation dynamics. It could be in the form of transfer functions, it could be just a single weight, and so on, or probabilities, for example. So I have not therefore labeled anything at the nodes, but overall there is a graphical model. And there are advantages of working with these graphical models. And the main advantage is the hierarchical representation. So if you look at the classical systems theory representation of dynamical systems, you encounter standard ODEs, PDEs, and so on. So you have to work with equations, whereas graphical models allow you to work without the equations. For example, you can just use this, you can feed this graphical model to an automated algorithm, which can then do a root equation. So just knowing the direction of propagation is good enough in many applications. And the graphical model allows you to do that. Then I can go one step further. In fact, one step back is not even knowing the direction, just knowing the association. I'll talk about that later. So there are different types of information that you can embed or encode in a network, which is not possible in an equation-like environment. Networks can actually be used for encoding equations also, like ODEs or PDEs and so on. And then you can account for a very important aspect, which I mentioned at the beginning, which is that a variable can play a dual role. Of course, even in systems theory, you can do that by means of feedback. But here in a network, it's very clearly brought out that a variable, if you assume that it is sitting at a node, effect, which allows obviously you to represent a large variety of processes, a diverse set of. Now, the challenge in working with network representations, especially when you have to reconstruct it from data, which is what I'm going to focus on in this talk today. We are talking of causal discovery. That means I have to discover this causal relation from data. And the biggest challenge, of course, is partitioning the variables into cause and effects. And associated with this challenge is a bigger challenge, okay, that I'll talk about very soon. In addition to partitioning the variables into cause and effects, you may have to sometimes associate weights to the relations, that means to the edges. So what I show you here is an unweighted directed network, but many a time you may be interested in reconstructing a weighted directed network. Okay, so these network representations appear in many fields, and they can be very complex. So I'm not going to go over these, but this slide should give you a flavor of the diversity of fields that are that subscribe to these network representations. And at this point, if you look at it from a distance, I want to say that, yeah, networks look the same. There are nodes and edges. But as I told you earlier, you have to be careful. When you choose to work with a network representation, you have to really ask yourself, what is it that I want to encode? What is it that I want to capture or represent? And unless you are clear about it, you will end up wasting your time, or you will probably come up with a model that is not suitable for your application at all, or you will end up making a wrong inference. So be careful, and the type of network that you choose depends entirely on the domain and the data generating process, and that will become clearer as we move on. By the way, I do like to keep this interactive, so if you have any quick question in between, do feel free to ask. Longer questions can wait at the end of the session. So we want to move from data to directionality. That is the causal discovery problem. Now, is causal discovery always related to a network representation of the system? No, not really. Network representation is a way of representing the causal inference. So you start with, let's say, some time series data, and then you ask some fundamental questions associated with causal inferencing. So if you assume Z1, Z2, Z3 here, as given here, this data is given to you, then some of the burning questions that arise are, does Z1 cause Z2? Is Z3 directly caused by Z1? If Z2 changes, does Z3 change instantly? And so on, right? So these are the questions that you try to answer in causal inferencing. Now, once you get your answers, it's up to you whether you want to represent this in the form of a network or not. Typically, it's convenient to represent this in the form of a graphical model. So one such representation is what I'm showing you here. There are many ways of representing this inference in the form of a graph. So the E's that you see here in each node, Z's are already known to you. The E is the endogenous excitation in each of these variables. So I'm assuming that each of these Z1, Z2, Z3 are stochastic signals, and they have, by their very definition, an inherent uncertainty. So the E1 is the inherent uncertainty in Z1, E2, and so on. And from the theory of time series modeling, we assume that E1s are white noise sequences, if not IID. But that is, as I said, one way of representing. In many parts of the literature, you will see, instead of E1, you will simply see Z1. And I find that not complete, because then it gives the impression that Z1 is exciting Z2. That's correct. But in many other representations, it may not be Z1 affecting Z2. It may be the inherent uncertainty in Z1 affecting Z2 and so on. So it's better to have everything stated explicitly. Of course, the weights tell you what it is. In order to go from data to a graphical model representations, of course, via the key step of causal inferencing, we have to answer some very key questions. What does cause mean? That's a very, very important question. Cause is a very qualitative term. Mathematically, what does it mean? Because after all, we are going to work with numbers. How do we infer? Of course, that has got to do with statistics. And what are the assumptions? What are the methods? Remember that there is, you may define cause in a particular way, and there can be, you may be subscribing to one definition of cause, but there may be many ways of inferencing it. So do not confuse them. Here that a lot of researchers are not clear, or they do not distinguish between the definition and the method of inferring it. They just simply confuse both, and then in the end you have a messy paper. And the question is, if you choose to represent in the form of a graph that you want to import. So a lot of questions you have to have clarity on before you jump onto causal discovery. Then the standard question people ask, people who are very fond of first principles modeling, they ask, why do you have to turn to data? Today, I don't have to answer that, but let me point out certain important advantages of turning to a data-driven method. Number one, you can calculate strengths of connectivity, which is very hard when you use a first principles approach purely. And very importantly, you can come up with what is known as an effective connectivity. So to give you a very simple example, suppose you live you take IIT Madras campus. If I look at the telephone network, right? So we are all connected. On paper, if I go to the telephone exchange, I know how the phone lines are connected. So I can draw a network of the telephone connections. But effectively, what is a network is I want to know. And that is what even many cell phone service providers are interested in. They want to know effectively what is the network, which subscriber is connected to many other subscribers, and then they use graph properties to figure out the most important subscriber and so on. Such effective connectivities can only be constructed from data. And this term effective connectivity has more or less emerged from neuroscience. Let me tell you that causal discovery is a very, very important branch of data science applications in neuroscience. The second advantage of working with a data-driven method is you can account for stochastic effects. And this is true not only in causal discovery, but elsewhere as well. It is not possible to account for uncertainties with a first principles approach. And finally, it facilitates inclusion of partial knowledge. And this is becoming a big thing today, right? We talked about physics informed and so on. So I know some knowledge from physics, and the rest I want to complete with data. That is another reason why you want to learn the data-driven method. So hopefully you're convinced now. As I said, when you want to construct a network representation, know your process, know your data. You have, like banks have KYCs. You have to go through, you have to think of KYP, know your process, know your data, know what you want to do, know your application and so on, and then make decisions. All right. Okay. So I just want to give you a glimpse of what are the different types of things that you have to worry about in a causal discovery problem. And this applies to even other aspects of standard modeling algorithm. Whatever I'm going to talk about, some of this applies to your standard data-driven model. Okay, so on the process side, we have to worry about whether the process is linear or non-linear, time invariant or otherwise, deterministic or stochastic. That makes a huge difference. Whether I'm interested in a direct or an indirect causal connection. And theoretically, whether the process has a unique network representation. It turns out that for many processes, there is no unique way of representing, representing it via a network. There can be many graphical models that can explain the same process. Then what is it that you're discovering this is a very open-ended and hot issue. People are yet to really get deep into this. On the data side, you'll have to worry about measurement error, sample sizes, minimal excitation. This is again an open area. People have not come up with any results on what kind of effects you have to perform, carry out in order to reconstruct the network effectively. And then you have to worry about missing observations, irregular sampling, and so on. Extensions to nonlinear systems are happening through either kernel ideas from machine learning or through usage of information theoretic measures like entropy and so on, transfer entropy and so on. And there are methods that detect both total and direct linkages. And as I said, uniqueness of network representations have been discussed only in very scarce manner. So that's again an open-ended problem. Okay, so since we are going to talk about data-driven methods, we have to be upfront very clear whether our data is belonging to an interventional class or an observed class. What do we mean by interventional data? Well, where you perform experiment, you intervene and you conduct an experiment and you generate the data. Whereas observed data is something that somebody else did the experiment for you and you collected it. And both situations exist, depends on the application. If you take atmospheric sciences, for example, there is no way you can intervene. You can't say, well, I'm going to increase the atmospheric temperature and see what will happen. Although we are doing that indirectly on a lighter note. But interventional data essentially means that with an objective, you have designed the experiment and you have performed it. Obviously, it has a lot of advantages because you're going to do controlled experiments, randomized experiments, and so on. But then practically, it is infeasible for many processes. And that's the flip side. Otherwise, if you can somehow intervene, perform an experiment, there's nothing like it. Observed data is the more practically encountered scenario where there is no user intervention. That's a flip side. And outcomes are recorded under routine operations. And the biggest the consequence of no user intervention is we have little or no control on the excitation levels or the randomization and so on. However, it's a highly practical situation, and somehow one has to work around and see what can be done. One of the things that we should also be able to say, given a data set, whether it is modeling or causal discovery, what is possible and what is not possible. That unfortunately people don't pay attention to at all in the frenzy of data science today. They just go ahead and build a model and then give the model without even giving a thought of what is possible with a given data. So please do pay attention to that before you jump into modeling or causal discovery. There is an issue with low generalizability and so on. All of that is understood, but I wanted your attention on these two classes, and you have to ask which one your situation belongs to. And sometimes it can belong to both. You may start with observed data, and then you may end up with interventional data. Okay, so I did talk about the different. Now we are turning our attention from data to networks. So we have data. We want to go up, go from the data world to the network world. And I did mention earlier that a network allows you to embed different layers of information. And here are 4 layers I'm showing you, but this is not exhaustive. One layer is simply association. So where you're only showing how the variables are connected, but unfortunately this suffers from confounding. But in many applications, I don't care. What I mean by confounding is I do not know whether the edge that I have drawn, for example, between Z1 and Z3, is it indirect or mediated? On the other hand, I want in many applications a confounding resolved network, but still I don't need the directionality. So we turn to what are known as partial methods. So you can strike an analogy with total derivative to partial derivative. This is direct or indirect, and then draw a graph. The next layer of information is the directionality, where we have figured out not only the direct, whether it's direct or indirect, but also the directionality. And we call this as the directed network. GC stands for Granger causality, but that's only one type of a directed network. The strength, and then the next layer is where I embed some information into the edge in the form of a weight or a dynamical system and so on. And we call this as a directed weighted network. Which network are you interested in? You want to figure out early on, depending on the application that you're looking at. And I'm just listing here different methods for reconstructing each of these networks. But before you begin, you should pay attention to this first banner here, which is asking you to think of the data generating process. Is it deterministic? Is it stochastic? Is it, if it is stochastic, is it jointly stationary? Are the methods or the statistics that you're assuming, do they exist? If there is deterministic, is it linear, non-linear, even stochastic, you have to worry. So many things you have to assume upfront before you proceed with any of these methods that I have listed here. Okay, so connectivity is the key in all of these 4 different forms of networks that I've shown you. And in neuroscience, there are 3 forms of connectivity that are very popular. One is called a structural connectivity, which is based on the first principles understanding of the, understanding of the brain from the scientific, from the medical knowledge. They're not relying on any data. Then comes a functional connectivity, which makes use of the data, but it doesn't, give you the directionality. And then comes the effective connectivity, which gives you the directionality as perhaps and as a weight as well. So to give you a picture, which I have borrowed from the source mentioned below here. Here you have what is known as anatomical connectivity, which is just a binary directed kind of network, yes or no, whether it's connected or not. And then you have functional connectivity, as I said, which is a weighted, undirected network constructed from data. So you compute the correlations and you apply a threshold to graphical model. Then you have the effective connectivity, which is both, which is weighted but directed. Functional connectivity is weighted. Effective connectivity is weighted directed network, where you use measures of connectivity that give you direction. So in this regard, I just want to draw your attention to a very interesting paper that unfortunately has not received much attention. This is a paper that appeared in 2009, which talks about the different connectivity measures and what are their properties and what is it that is desirable. So a connectivity measure typically should have, if you read the paper, it talks about these three important properties that are associated with the metric, namely reflexivity, symmetry, and triangular inequality. Reflexivity has got to do with when you measure, when you apply the metric to the same variable, between the variable and itself, it should come out to be zero. That is what is the definition of, or the demand of a reflexivity. For example, correlation doesn't give you that. Correlation between a variable and itself is 1, but you can modify the definition if you wish to bring about reflexivity. And if you can do that, then the symbol that is used in this table is O. It says that you can modify it to bring about that property. Symmetry, we all understand. Correlation, for example, between X and Y is the same as between Y and X, and therefore has a plus sign. The main problem here is if you want to use use a measure that gives you the direction, then you cannot choose a metric that has symmetry. That is why this table is important. It tells you which connectivity measure you should pick depending on the network that you want to reconstruct. If you're only interested in an undirected network, then you can go ahead and use covariance or correlation, or even mutual information for nonlinear systems. Whereas if you want to use if you want to reconstruct a directed network, then you have to use a measure like Granger causality, or let's say imaginary part of coherency, or other methods that have come up in the recent times. I don't consider this table as very exhaustive, and the authors also say the same thing, that it is only based on some popular measures. Then reflexivity is desirable in many applications, especially for it to be qualifying as a metric. The triangular inequality has got to do whether it can cater to confounding or not, and so on. And Granger causality, yes, it can. It measures a direct link, therefore it satisfies the triangular inequality principle. Correlation does not, because it suffers from confounding. It cannot distinguish between direct and mediated effects, but it can be modified to come up with partial correlation, and therefore you have a zero. So I hope then now you can apply this to the rest of the table. This is, my intention is not to go over each row of the table, but I have given you, I think, the necessary ammunition to read the necessary material to understand the rest of the paper. But the purpose of showing this slide is to again tell you that the metric or the measure that you choose has to be commensurate with the type of network that you want to reconstruct. By the way, I mean, I did want to also draw your attention to a distance measure known as the Wasserstein distance, which is, you can see it as plus in all, right? Which means that it respects the given property. And it is the most suitable candidate according to the authors, and it is also documented well in the literature. Then why don't people use this? Then because it has two problems. Computationally, it is very costly to compute. And third, and then secondly, it can be quite robust, quite sensitive to the presence of anomalies or outliers and so on. There is some work that is happening to fix those, but then my feeling is that you may end up compromising on some of the properties. But all said and done, Wasserstein distance apparently is now becoming more and more popular in machine learning to figure out associations and directed connections. Now let us come to the main point here of determining and defining causality. And obviously, there are challenges there, as I mentioned. So determining cause of an effect is obviously much more difficult than studying effect of a cause, right? You will agree with me. If I give you some phenomena, ask what led to this, it's going to be very difficult. But if I give you, let's say, temperature and ask you to study its effect on the pressure of a gas, yeah, it's possible to do that. And what is even more challenging is defining a cause. And most of the literature is devoted to studying effect of a cause. So does it mean we can never determine if X causes Y? Yes, we can, but in a backdoor way. That means you assume that X causes Y and see and test for it. Okay, which means that I can never figure out all the causes for Y, but I can pick one potential factor and figure out what to do. And that's what we normally do. Assume X to be the cause and determine if it affects Y. But the challenge there again is X could affect Y in many ways. It can affect its amplitude or mean or variance or distribution, or in many chemical processes, biochemical process, X can only be a trigger. It just triggers and keeps quiet. So how do you figure out that is a difficult proposition. So what are the notable definitions of causality? I've collected a few popular ones for you from the literature. So you have, of course, the Granger causality sitting at the top. Normally, I would give you some stats on it, but I didn't do it this time. You can figure out, you can go to Google, search any internet resource and search the combination of, just search for Granger causality and you will see millions of results. So what is the Granger causality based on? The idea, it's a very simplified one. We'll go into detail very soon. We say X, Granger causes another signal Y if its past aids in improving prediction. So it's set up in the prediction framework. However, the issue is that it assumes the process is stochastic and it assumes a temporal precedence of the cause, which is not so bad, but there are other limitations and issues. By the way, it detects direct causality. On the other hand, there is a causality due to Sims. Sims is the name of a researcher in social science, who proposed similar causality measure, similar to Granger causality, but the only difference is it detects total causality. Otherwise, everything is the same, and therefore it suffers from same issues as that of G's. Then you have what is known as interventional causality, which is you will find in the Julia Pearl school of thought and other schools of thought that focus on only random variables. We worry about signals, whereas there is a section of the literature that is devoted to causal connections between random variables. And this do notation is due to Julia Pearl. Basically, do says you will have to intervene and you will have to set the value of the potentially causal variable to some value, and then examine the conditional probability of Y. If the conditional probability of Y given the intervention is not equal to the unconditional probability, then we say, yeah, I causes Y. Again, it is probabilistic definition. Unfortunately, no extensions to signals are available. You can, but very difficult to implement because it requires intervention. Then you have counterfactual causality, which is more of an imagination, I would say. The question that you want to ask there is, based on which you arrive at causal inferences, you ask what would have been the influence of X on Y had X taken a different value. That's very difficult. In many cases, it's not possible to even implement that scenario. So highly difficult to implement. Then comes the cross-mapping causality, which is what I'm going to talk about briefly today's talk, where you see in the top row stands Granger causality, which looks at if X aids in improving the prediction of Y. And cross-mapping looks at the reverse. It is asking it's saying that if X can be recovered from Y consistently, then you can say X is a cause. That means the DNA of the premise is the DNA of the cause is there in the effect, and you should be able to recover X considerably well enough from Y. But of course, it also has its own limitations and so on. It was originally introduced for nonlinear processes, deterministic signals, and so on. It's not so clear how it works for stochastic signals. The definition may have to be modified also. the original definition of cross-mapping causality does not resolve confounding for you. And I'll present one such solution towards the end. So here is a graphical picture of the literature. I'm not going to go through every node of this graph here, but it suffices to say that the causality identification methods can be classified into that of stochastic and deterministic signals. And then there are different definitions catering to each of these. As you can see, for deterministic signals, the work is relatively much less as compared to for stochastic signals. Okay, and that tells you what are the research gaps. It doesn't mean that the stochastic signal world is saturated. No, it continues to evolve, and you can certainly contribute a lot. In general, the frequency domain methods are advantageous over the time domain counterparts in a few respects. I'll talk about that very briefly. And the methods for multivariable or nonlinear processes have only recently been implemented. Okay, so let me now spend the next maybe 20 minutes at least on 15 to 20 minutes on linear Granger causality, or shortly known as Granger causality. I've already explained to you the basic idea or the basic premise. It stands on three axioms. Cause precedes the effect. Cause contains unique information about the future values of the effect. And all causal relationships remain constant in direction throughout time. Now, the first one has got to do with temporal precedence. The second one, uniqueness, very difficult to verify. Third one, if it is violated, you can use an adaptive or a time varying approach to figure out, to catch up with changing causal relationships. But the first one is suppose if and cause are instantly related, then you have to be careful. There are some workarounds, but no complete workaround for violation of axiom law. So if you look at Granger causality, and I must caution you at this point, when you search for Granger causality literature, unfortunately, you will be led to many, many presentations of Granger causality that give you such diluted versions of it, to the effect that they don't even give you a definition that is commensurate with what Granger has proposed. They straight away go to the implementation of Granger causality. That is a completely different matter. How you test for Granger causality does not constitute its definition. So if you're reading an article that tells you how to test for Granger causality, keep it aside for a while and go and search a paper which tells you what is Granger causality. So Granger started off with information, and he said, let I star represent the information set up to K, and I star minus Zi, information excluding Zi, because you want to test if Zi causes Zj. If the Zj at K plus is a future value is conditionally independent, that is, if whether you include Zi or not, it doesn't make a difference to the future of Zj in terms of information. Then, in fact, then we say the series that does not Granger cause, else it Granger causes the series. So you can see Granger started off with information. There is no prediction coming at all here. Gradually, he changed it into probability. So he said, if the conditional distribution of Zj is unaffected by the inclusion or the exclusion of the past of Zi, then Zi is not Granger causing Zj. Okay? But then that also became very difficult to implement because conditional distributions, as you know, are very difficult to estimate. Therefore, Granger had to do something. And in addition, it is not possible to measure all the variables relevant to Zj. You cannot get the universal set. So a working definition that includes available knowledge was provided by Granger. When he said that, suppose you have observed Zi and Zj, and another set W, which is potentially affecting Zj, then conditioned on W, you can say Zi Granger causes Zj if again the same story, the if the information, if the future values are unaffected in respect to probability distribution. Okay. So essentially what was required was test for conditional independence, but that also is very difficult to implement in practice. Not impossible, but quite cumbersome. So Granger replaced it with tests of prediction. That is how the prediction-based definition came about. Unfortunately, many parts of the sections of the literature don't focus on this and then simply jump straight away to this, which is okay, but then a holistic picture is missed out on. So what is the idea? You predict Z2, let us say, using its own past, you construct prediction 1, excluding Z1. And now you construct another prediction of Z2, you including the past of Z1. If the forecast is improved, then we conclude that Z1 Granger causes Z2. That is the idea. So if you construct, essentially you're going to construct these two models here, just as a simple example. You don't always stick to this kind of model. Granger doesn't talk about what kind of models you should build, although he later on very quickly advocates the use of what are known as vector autoregressive models. So E1 and E2 represent the uncertainty or the leftovers after you made the predictions in each of these two models. If sigma square, or in fact, I would say sigma square, you can say epsilon 1 is what you have as a residual or the prediction error. If sigma square epsilon 2, which is the residual obtained from the second model, including the past of Z1, if that variance is less than sigma square epsilon 1, then Z1 is said to Granger cause Z2, and then you draw a Granger causal graph as I've shown here. And you can extend this to multivariate and handling by feedback, that is bidirectional causality and so on, and to a certain extent accounting for instantaneous causality. I will not talk about the instantaneous causality part in today's talk. But the important thing is the definition is not tied to a method of prediction. Keep that in mind. So once you figure out the Granger causality between variables, then you draw a Granger causal graph. So you can draw a Granger causal graph even if you're given the mathematical model of the process, by the way. You don't have to be given data all the time. So if you're given a model of the process this way, then straight away applying the Granger causal definition, you will be able to draw. I mean, you can draw this Granger causal graph here. And remember, it only tests for direct effects. So you can see that Z1 directly affects Z3 and Z2 directly affects Z3. That's what we mean here. And Z1 and Z2 are not coming. Now comes the test for Granger causality. That is very important. There are many tests that have come up since the introduction of this definition of Granger causality. There are variance-based tests. Remember, we just said all we do is compare the variances of the prediction errors. And I'm not going to go over each of these tests. This is for your information. Then there are model-based tests, which is very, very popular. What you do is, instead of comparing the variances of the residuals, you place your attention on the model and then apply certain significance tests on the parameter estimates of this vector time series models. I'll show you very soon. And then you conclude whether Z1, Zi affects Zj. Then there are other methods based on what are known as partial directed correlation. And then you have the frequency domain methods, which are very popular. So you have given time domain data, but you work in frequency domain. And there are two very popular methods, one being more popular than the other. The partial directed coherence is more popular. This is due to Bacala and so on. And direct pathway function is something that we have introduced from our research group. And there are advantages of using direct pathway function over PDC, but both give you the structural information. So the model-based one is a very popular one, and that's why I very quickly want to describe that, so that when you want to implement, you can use this approach. What you do is you build what is known as a vector autoregressive model for the given series. So you're given a 5-dimensional series data, let us say some 1,000 data points or 2,000 data points. You fit a VAR model known as a vector autoregressive model of a suitable order. You use Akaike information criteria or some information criteria to figure out the suitable order. And the goal is to get these A's and variances of E. In a model-based method for Granger causality, you draw your attention to, you focus your attention on this matrices AR and ask if I pick a particular row which corresponds to a variable and examine the coefficients associated with that row and all the other variables. Suppose I want to look at the causal relation between, let's say, Z1 and Z2, whether Z2 affects Z1. Then I look at all the coefficients corresponding to the lagged versions of Z2 in the first row. If all of them are 0, then I conclude Z2 doesn't Granger cause Z1. And then you apply this to all other variables. But what are the assumptions? You're assuming that the process, data generating process is stochastic, it is jointly stationary, the spectral density matrix is factorizable, and on top of it, that the VAR model is a suitable representation of the process. We have shown in other published works, and people have also talked about it, that if the data generating process is not appropriately representable by your VAR model, that bias can obviously introduce a bias in your inference. Now, I did tell you that the frequency domain measures are very popular. So from the VAR model, you can construct what are known as frequency domain measures known as partial directed coherence. Again, this is a topic in itself, but I'm just giving you the expressions, and there are MATLAB routines, toolboxes available to calculate this for you. The idea is once you construct your partial directed coherence, then you come to the conclusion that the inference that method is if the PDC, squared PDC, the PDC is a complex valued number, the squared magnitude of the PDC is 0 at all frequencies for a pair of variables, then you conclude that Zi does not Granger cause Zj. Okay. On the other hand, instead of using VAR models, you can use VMA models, known as vector moving average models, which are slightly more difficult, cumbersome to estimate, but not impossible. Fairly okay. So if you estimate a VMA model, then you can directly come up with the Sims causality, interestingly. And again, you can work with frequency domain measures. That will allow you to figure out both the total causality as well as the direct and indirect. So the total causality given out by Hij of omega, which is constructed from your VMA model, can be actually split into direct and indirect pathways. And this is in one of the published works that we have shown in a paper that we published in cybernetics, biological cybernetics. And you can show that once you split it into direct and indirect pathways, the direct transfer function serves as a measure of Granger causality in frequency. And from that, you can construct what is known as the direct pathway function. So that is the idea. So this direct pathway function is a measure of Granger causality between Zj and Zi. And the nice thing is it allows you to calculate the strength of connectivity. The reason is, unlike PDC, which connects Zj to Zi or Zi to Zj, the direct pathway function connects the inherent uncertainty in the potentially causal variable, that is Ei to Zj. That is the big difference between PDC and DPM. So let me just walk you quickly through a simulation case study. So I have 1,000 observations of a 3D stationary process. And the goal is to reconstruct a class of networks, starting from undirected and so on. So we primarily use frequency domain measures, and one such frequency domain measure, which is equivalent of cross correlation function, is coherence. So I'm showing you the coherence function for these three variables. It's a 3x3 plot shown in pairs. The diagonals is a coherence between the variable and itself. That obviously works out to 1. Some of you may be familiar with coherence. Coherence is a measure of linear relationship between two variables at each frequency. That you can, I think that suffices for now. So the idea is if coherence is non-zero at any frequency, then those pair of variables are affecting each other and in that direction. So the columns act as sources and the rows represent effects. So in coherence plot, unfortunately, there is no distinction between source and an effect, and therefore you can only draw a graphical model that is undirected. It's a symmetric plot. On the other hand, because coherence suffers from confounding, that is, I'm not able to say whether this is direct association or indirect association, we can come to what is known as partial coherence. The x-axis is same as before, frequency. And the partial coherence confirms that all these relations are direct. Remember, I'm only using the data here. I'm not using any knowledge of the process. Then I have this partial directed coherence that is talked about, which is constructed, estimated using the VAR model. And now you can see it's an asymmetric plot here. X-axis is the same, frequency, the interpretation is the same, except that it is an asymmetric measure. And from this, you can infer the dashed line represent the significance levels, and you can infer the directionality. Beautifully, the bidirectional thing has been figured out. Okay. So now the PDC is telling me that both Z1 and Z2 affect each other, whereas Z2 affects Z3. Again, Z2 and Z3 affect each other. The direct pathway function, which has the same interpretation, also gives you the directed network, but gives you the strength of connections. So it says that the strongest link, perhaps, is the connection between Z1 and Z2 and vice versa, and maybe Z2 and Z3. The weakest link, in fact, is between Z1 and Z3. So how does it tally with the true network? So this is the true causal network with the weights, and this is the identified network, and you can see it has been figured out very nicely and accurately. Of course, the weights have some error in them. This is the data generating process for you in case you want to simulate all E1, E2, E3 are Gaussian white noise processes with mean 0 and variance. Okay, so hopefully you got a picture of how things are implemented. Now, as I told you earlier, Granger causality has its own limitations. And there are a number of limitations I've listed here. And I talked about this, right? For example, stochasticity is a major limitation. It cannot handle deterministic signals. Granger himself declares that very openly in his seminal paper in 1960s. And it is sensitive to measurement errors. And if you downsample, then you can get spurious connections. And there is no direct provision for detecting instantaneous causality and so on. And I did mention about the model misspecification part. Some of the commonly misunderstood limitations, which are not correct, is that it is applicable to linear processes. No, Granger never mentioned that. So if you read a paper which says this, don't accept it. It is only based in the predictive framework. No, it's popularly based in the predictive framework. No room for handling non-stationarities. That is also not completely correct. So don't buy these simple limitations. I'll just illustrate some of the limitations and then move on to, and then talk about some remedies and then quickly move on to convergent cross-mapping. So here we have a 5-dimensional process, and this is the true Granger causal graph. So you can, from the given model, you can figure out what are the Granger causal connections and draw this graph. Now, suppose I omit, let's say, 1, 4, and 5, and analyze the causal connection between 2 and 3. Interestingly, you can see, if you look at 2 and 3, there is only one unidirection between 2 and 3. But if you analyze 2 and 3 as a pair, then you come up with the with an additional connection which goes from 3 to 2. Okay, so there is a problem there. Likewise, if you just take 3 and 4, so what is happening is confounding here. You are suppressing the knowledge of other variables. Then you see the dotted line here represents instantaneous connection. That is also detected. And likewise, you get some graphical relationships or causal inferences that are not necessarily commensurate with the full graph that you have. Okay? I am not going into great detail, but the message is that the subgraphs derived from data do not necessarily tally with the subgraphs that you derive from the graph. They both have to tally. And in order to address this, Eichler, who has made some very important contributions to this topic, to this field, proposes the use of what is known as a mixed graphical representation. I don't intend to go that into detail. You can refer to this reference. So this is one limitation. Then the second issue that I talked about is handling missing data. So how do you handle missing data? Well, There are so many solutions. One very popular and modern solution is based on the ideas from compressive sensing. For those of you who are familiar with signal processing literature, compressive sensing is a very modern, relatively modern field. That's about, I would say, 13 years old. That has taken a lot of fields by storm, and it's based on the idea of sparse representations of signal. Compressive sensing is about sensing signals in a compressed manner online. But then once you compress, you have to worry about recovering. So compressive sensing is both about sensing in a compressed way and then recovering from the compressed form. So encoding and decoding. Now that encoding and decoding is based on what are known as sparse representations of the signals. And what we mean by sparse representations is that you can represent the signal using very few atoms. I don't want to use the term basis because basis confines things, restricts things mathematically. More suitable word is dictionary. A dictionary is like your standard dictionary that you use in your language. So your signal is assumed to be linearly representable in some dictionary. And when we say that it has a sparse representation, that not all, only few words in the dictionary go in constructing that signal. That is what we mean by sparse representation. So we use that here in order to handle missing data. It is used elsewhere also in all other applications of handling missing data. After all, recovering a signal from a compressed version is akin to recovering missing data. So another way of looking at it is we estimate the models, not like the VAR models that I just talked about, not just using least squares method, but using regularized least squares or penalized least squares. That is another way of looking at it. And then once, so what you do is instead of reconstructing the signal, first we recover the representation. And once the representation is discovered, then the signal is reconstructed. That is the idea. So this is a procedure. I don't intend to go through every step, but we use a two-step procedure to construct our dictionary. The dictionary for the signal is also not known. We assume initially that the signal is representable in the DFT basis, and then we use the past values of the signal after a first level reconstruction to improve or to come up with a composite dictionary here that you see, and then refine our reconstruction. So just to give you an example on climate data here, you can see you have meteorological time series. This is real data. We introduce missing observations deliberately, about 30%. And note that missing data is at different locations for each signal. And we have the reconstructed signal here coming up from method. And this is the normalized direct pathway function from which you can reconstruct the network given. So you can tally, for example, you can conclude that Z2 doesn't affect Z1 or S1 doesn't affect S2, S3, sorry, doesn't affect S1, whereas S1 affects S3. So you can complete the rest of the picture here. And for comparison, this is the true network with the strengths. Obviously, because of missing data, some of the weights are not estimated fairly accurately, but the directionality has been well resolved. And I just want to conclude the discussion on Granger causality by pointing to a method that we recently developed for basically, I would say 6-7 years ago, for handling nonlinear processes. And not just our method, there are many other methods that are based on transfer entropy. So instead of using standard correlation-based approaches for the linear world, you use transfer entropy. Or you can use information theoretic based measures or correlation integral, or use kernel based ideas, which is what we have used. So idea, in kernels in machine learning, one way of using kernels is for handling nonlinear classification, nonlinear regression, and so on, is to generate features from data and then work in the feature space. The beauty of using kernel-like functions is the covariance between features can be calculated by working with the data alone without knowing the explicit feature transforming function. That is the basic idea, the basic trick. So we know, I'm going to skip this slide. I've already told you why, and it's pretty clear as to why we want to turn to nonlinear methods. But one point that I want to mention in favor of kernel-based methods is it has the simplicity of a linear tool, because you can compute the correlation in the feature space by working in the original data space itself without having to explicitly generate the features. That is what it is. And the main idea comes from a work by Santa Maria in 2006, who proposed this function called core entropy. Essentially, it is an autocorrelation in the kernel space. That suffices for now. And we use a Gaussian kernel, a very popular kernel, to carry on. That RKHS stands for reproducible kernel Hilbert space. So I'm going to skip the math. You got the idea. What we do is we work in a feature space, and the rest of the story is the same. We build var models in the feature space, and the var models can be estimated using only covariances, and the covariances between features can be calculated by working in the original data space. So the autocore entropy that I just introduced has the same interpretation of an autocovariance function, and the only thing is it considers only even moments. Remember, nonlinear relationships can have actually, they are characterized by the PDFs, which means you have to look at all the moments. Whereas for linear processes, it suffices to work with up to second order moments. Because this autocore entropy is encapsulating higher order moments, it is able to cater to the nonlinearities, but not all classes of nonlinearities. And the main result is for an independent stationary process, an IID process, the autocore entropy is independent of the lag. Compare this with the autocorrelation for a standard stationary process, white noise process. The autocorrelation is 1 at lag 0 and 0 elsewhere. So this is slightly different. VL is the same as V0. It's a flat autocore entropy if the series is IID. And you can extend this now to cross core entropy as well. So just show you an illustration on the Lorentz attractor, the very famous one. Even Sayan talked about it yesterday. So here is the equations describing Lorentz attractor with these parameters. And I'm just showing you how the autocore entropy is much better suited at analyzing nonlinear dynamical systems than the autocorrelation. Look at the autocorrelation plot that we have for each of these variables. Assume x, y, and z are measurable. Then you compute the autocorrelation. You can see that perhaps x and y are in sync, but not z. But we know they are coupled, right? Whereas the autocore entropy shows this coupling very nicely. You can see that the autocore entropy of all x, y, and z vary in the same way, and instantly telling you, very straight away telling you that they are coupled. Okay. So what is the idea now? As I told you, we extend this idea to construct PDCs in the kernel space. So if you have not followed anything, the bottom line is, instead of working in the data space, we are working in the kernel space. The rest of the story is the same. We build var models from which we construct PDC and so on. So let me show you a quick implementation here. We have a nonlinear bivariate process. E1 and E2 are white noises here, and I've given the values of S, A, and C. You can simulate the data for yourself. This is what the classical PDC will tell you. The dashed lines are the significance levels. It tells you that, gives you the impression that x2 affects x1. Okay, but you know from the equation that x2 doesn't affect x1. That's because we have used the linear measure. On the other hand, if you use kernel PDC, which works in the kernel space, it's pretty, it comes out correctly. These dashed lines, by the way, are constructed using bootstrapping methods, and I'm not going to talk about that now. Another case study of a bioreactor. You can refer to our paper for more examples, but I'll just conclude with this example, this particular topic. We consider a 3-state bioreactor model, and the mu which is the growth rate, is a function of x3 and x2, right? So which means that, here whatever is mu, x3 and x2 affect x1, and all the parameter values are given here. So once you construct the kernel PDC, it comes up with the correct picture. Of course, we have done a very detailed analysis, type 1, type 2 errors, and so on. You can refer to our paper. But bottom line is it's able to handle the non-linearities very well. Okay. So I just want to conclude this topic on Granger causality by pointing out its limitation in engineering applications. I did mention this, that it is suitable for signals that have stochastic variations. So here I consider two simple liquid level systems in series. What I mean by that is flow. There are two tanks placed in series. The output of the tank 1 is the input to tank 2. Okay, so that is what is the setup. And we introduce excitation in the inlet to the first tank. And A1, A2 are the cross-sectional areas. We assume cylindrical tanks. There are valves at the exits of each tank. These are valve coefficients. And the steady state values of the levels are given here. The steady state value of the inlet to flow is given here. So we introduce two different types of excitation and ask a Granger causal method to figure out the network, right? So unfortunately, if I apply the Granger causal network to a pulse type signal excitation generated data, then it comes up with the wrong one. But if I introduce a stochastic signal, stochastic excitation in inlet flow, it comes up correctly. Because we know F0 affects H1 and H1 affects H2. This is the correct network, right? Whereas you have spurious connections coming up. And that is because of the fact that the GC-based definition, and therefore all the methods are not suited for deterministic signal, deterministic variations in the signal. And on top of that, measurement errors can actually take Granger causality for a ride. Okay, so that concludes my overview of Granger causality. I'll just spend about 10 minutes on convergent cross mapping. And the ratio amount of times that I have apportioned are also perhaps in the same ratio as the number of years for which Granger causality has existed as against convergent cross mapping, in fact, perhaps more. So what is convergent cross mapping? Why are we turning to that? Well, we just saw that Granger causality definition and the methods are not suitable for deterministic systems. Nonlinear, yes, it can, but mainly deterministic systems. So taking this as a motivation, Sugihara, in a very in a pioneering work that appeared in Science, proposed a method known as convergent cross mapping. And to understand this method, maybe 2-3 minute basics of nonlinear dynamical systems are required. So here is a single slide that gets you the hopefully some of those basics in place. Here is an autonomous deterministic nonlinear dynamical system. You cannot break it up into parts, right? Like you are able to do in a linear system. That is the functions here cannot be written as a superposition. This is the continuous time version. This is the discrete time version. Obviously, to different initial conditions, you'll get different trajectories. And if you were to plot all the trajectories for all possible initial conditions, and if it is so-called dissipative system and so on, then you get a phase space plot. I'm assuming a three-dimensional, three-state system. Now, so what we are given is data. We are not given this model. So how do we go about figuring out how many states are required? What is the causal connection between these states is the objective. In order to answer the causal connection, causal discovery question, we have to somehow reconstruct the state space or some image of it. That is the idea. And for this, the notion of manifolds and embedding are central. So what is a manifold? It's a topological space that locally resembles a Euclidean space. There is a lot of deep math in it. But to give you an idea, a sphere locally looks like a circle. Okay, a sphere is a 3D here, a circle is 2D. So the original space is 3D, but locally it resembles a circle, which is in the 2D. Like, or if you take a circle locally, it can be mapped to a line and so on. So when you have a space, a topological space that has these characteristics that locally it resembles a Euclidean space. We call it as a manifold. And dissipative systems can basically qualify for such manifolds. That's the idea. So how do we reconstruct? What is the role of this manifold and how do we reconstruct is what I just want to spend a few minutes on. The central idea is to construct what is known as an embedding. And by the way, for those of you who are familiar with state space identification of state space models, this may seem very similar. There is only one paper that talks about the connections, but by and large, the nonlinear dynamical systems literature that talks about embedding, unfortunately, does not establish the connection between the state space reconstruction here and the state space reconstruction for linear systems. We do plan to write a tutorial article on that very soon. So an embedding is the key to reconstructing a state space or an image of it. And what is an embedding? It is essentially, in a very strict mathematical term, it's a one-to-one immersion or a smooth diffeomorphism of M. One-to-one, we understand. It's a unique mapping. Essentially, diffeomorphism means that the derivatives are also mapped one-to-one. That is what we mean. And this is, how do we construct such an embedding? That is the idea. Once you construct an embedding, then you can answer questions pertaining to causal discovery. That is what Sugihara showed. But the key is to construct an embedding. That is a diffeomorphism, a smooth diffeomorphism of the original manifold of the process. So in this regard, there are two milestone theorems due to Whitney and Takens. So what Whitney said is, assume that you have measurements of the states. States, by their very definition, are not necessarily directly measurable. Generally, you measure state, a function of the states or a projection of the states. For example, you may have a temperature and liquid level and so on, but you may measure only temperature. Or there may be other cases where you are measuring a combination of states put together if they are of the same physical meaning and so on. So the main point here is what you have with you is measurements S, which are projections or functions of the states. What Whitney assumed is you have many such different measurements. We are not talking about measurements in time. Yes, that is different. So he said that you have many such different functions of states that you are measuring. And if you have that, and if you stack them up this way, then you can construct an embedding of the original manifold. That is what it is. How many such measurements do you need? You need 2D plus 1. What is this D? D is the dimension of the one that we talked about here, right? Of the manifold. Typically, D is referred to as a dimension of the manifold. So you may not know D upfront, by the way. So that is one big headache in using Whitney's embedding theorem. And the other disadvantage is you need so many different sensors. Takens, and this was way back in 1930s, Takens made a very important contribution in the 80s, where he said, you don't need that many sensors. You just need one sensor reading over a period of time, and you stack them up using the past data. This is the idea that you will also see in the state space reconstruction for linear systems. Basically, you turn to stacked past and then recover the full state space. How many lags? What is the lag that he is referring to? Tau. That is, you want to stack up S at this instant, the measurement tau minutes away or tau time instants back, 2 tau, and so on. And then how many such lags? D such lags. Okay, 2D. In fact. So, sorry. So that's what Taken proved, that you need 2D such past values to construct the embedding. How do you know D? You'll have to figure out. How do you know tau? You'll have to figure out by trial and error. But at least it's great because I don't need that many sensors. And then, unfortunately for fractals, D is not an integer. It can be a non-integer and so on. So you'll have to worry about that a bit. Then people went ahead and combined this Taken's theorem as well as Whitney's theorem and said, look, let us use apply this to multivariable systems where you are measuring more than one variable, and that again is due to Sugihara. So we have used this method very recently to come up with causal discovery in multivariable nonlinear systems, which I'm not presenting here. One is the reason of time, and other is if the work is under peer review right. So once it gets published, of course, you can look up the literature. Okay, so primarily Sugihara's work on convergent cross mapping uses Taken's theorem alone, not his generalized theorem. Unfortunately, he didn't use his generalized theorem for multivariable reconstruction. So what is the idea? I'll tell you in a minute. Just want to give you a feeling of how an embedding is constructed. I take the familiar Rossler attractor, and the way you do is there are methods to figure out what is an appropriate tau and what is an appropriate embedding dimension, M or D. You compute what is known as self-mutual information for different values of tau. Mutual information, remember, is a measure of nonlinearity. What you're doing is you're asking how much is the lagged version related to the current signal, how many lags are required, have you exceeded, and so on. Have you over constructed, overestimated the lag, and so on. So you try out different values of tau and compute the mutual information. The first minimum of the self-mutual information function versus different values of tau is recommended as a good value of tau. So for this Rossler attractor, it turns out that 138 is a good value. This 138 has a meaning. It is 138 sampling instance, remember. And then how do you determine the embedding dimension? Again, you use a method called fraction false neighbors. I'm not going to go into the technique, but what you do is you compute what is known as a false nearest neighbor, or fraction false nearest neighbor index, and plot it versus different guesses of embedding dimension. You pick the first minimum. In this case, the first minimum occurs at 3. In fact, it stays flat thereafter. So this is similar to your many other plots where you don't know the order of the polynomial, and you use an elbow or a scree plot to figure out what is the order of the polynomial, or what is the number of principal components you require, and so on. So for this example, it turns out the embedding dimension is 3, and this is the original manifold, and this is the reconstructed manifold. Yeah, you may say, oh my God, there is so much of a difference. But the point is not to get this exact manifold as is in terms of the shape, but what should be guaranteed is certain properties of the manifold have to be preserved. Your reconstruct manifold should have the same properties. For example, there is something called a Lyapunov exponent. That should be the same. The manifold dimension should be the same, and so on. So that is guaranteed by virtue of Taken's embedding theorem. That's the beauty of Taken's embedding theorem. Okay, so very quickly, let's converge to convergent cross mapping. The idea now is based on recovery. What Sugihara suggests is if X causes Y, then there should be enough information about X encoded in Y, but not the other way around. So how do you recover X from Y? You go to the manifold of Y. I'm just showing here, assuming the dimension, the manifold dimension is 2. So you go to the manifold of Y, and you identify points that are nearest, and then you recover X based on those points that you have identified that are very closely situated in the manifold of Y. The guarantee, or the premise rather, is that if there are points close in the manifold of Y, then you will be able to recover X very well. So you can see that here. So the bottom plot shows points that are very close within the manifold of Y, and then you are able to figure out the points that this is the Y1. From Y you go to X. There are points that are very close here. If based on these timestamps, you figure out what are the points that are very close in X, and then you recover X. If X causes Y, this is what is going to happen. But the reverse is not going to be true. That is, points close in X will not correspond to points close in Y. That is the bottom line. Okay, so the idea is, of course, you do not know upfront whether X causes Y or Y causes X. So you try both and then you recover. And what do? Essentially, you do this recovery for increasing sample size. As you increase the sample size and you recover, you also compute the correlation between the recovered signals and the given time series. So that is what is being plotted here. So CMS stands for cross map skill. The x-axis is library size. The blue line is the correlation between the recovered X and the original X for increasing sample sizes. You can see that correlation hits 1 for large sample size, whereas the correlation decreases and almost settles to an insignificant value for the case of recovery of Y. So you conclude that X affects Y, and that is indeed the case. I'm just showing you the case for the plots for known cases. If X and Y are affecting each other, then both cross map skills will be very high as you increase the library size. And finally, if they don't affect each other, the cross map skills are going to be poor with the increasing library size. So two things I just want to talk about. I just take 2 minutes. One is the effects of measurement noise. Unfortunately, Sugihara's work and later works do not address the effects of measurement noise. They were only focused on the non-linear aspects of the dynamical system. But what happens, obviously, you know, when there are measurement noises, the signal to noise ratio can affect your cross map skill. And we show here a plot of the cross map skill for different signal to noise ratios. And you can see that when the signal to noise ratio is very low, like 0.9, the cross map skill is bad. Whereas when the signal to noise ratio is very high, the cross map skill is quite high. So obviously it is sensitive to the signal to noise ratio. What we do is, in order to determine if the cross map skill is significant, ultimately it boils down to a hypothesis test that that corresponds to significance of cross map skill. So if the null hypothesis X does not cause Y, we generate surrogate data corresponding to that null hypothesis using a technique called phase randomization. Essentially, it kills any possible connections between X and Y numerically. You do a Fourier transform, randomize the phase for each of these variables, and then reconstruct back, you would have killed all the connections. That would correspond to the scenario of the null. And you do this for different randomizations, generate different surrogates, and then you pick the quantile, 95% quantile, and you plot the cross map skill. Okay, so what you do is, this is a 95% quantile, and you plot the cross map skills for different library sizes, and you see if it is for most of the library sizes, particularly for the large ones, is it above or below this line? And here, although I'm not showing the library sizes, for large library sizes, is the ones that correspond to these points, and we conclude that the cross map skill is significant, and therefore we reject H0 and then come to the inference that X indeed affects Y. So finally, unlike Granger causality, convergent cross map does not detect direct links. It only detects total causality. And to illustrate this, I have a 3-variable process here for you, which you can use for simulating. And the variances of E1, E2, E3 are adjusted such that the signal to noise ratio is very high. So that doesn't come in the picture. This is the true network structure, and where the edges are denoting direct connections. We are interested in direct connections. If you are interested in total connections, then you can skip this part of my talk, the remaining 30 seconds. So when you apply the CCM here, when I'm showing you recovery of variable 1, that means recovery of Y1 given Y2, given Y3, Y2 given Y1, given Y3, and so on, you can come up with different possibilities here. Of course, what you can clearly say is Y1 affects Y2, Y1 affects Y3. Yes, that is one possibility. The other possibility is that Y2 affects Y3. Maybe there is a direct connection. That's the second, not other possibility. Additional inference that you draw is Y2 affects Y3. So we have to somehow combine these two. In the first one, there is an ambiguity. I'm not so sure, given this second possibility, whether Y1 affects y3 indirectly or directly. That is not clear. So to resolve that, we proposed a regression method where you regress recovered the original y1 on the recovered y1s. Remember, we have y1 recovered from y2 and y3. So those are the regressors, and we regress the given series y1 on these two recovered ones with the hope that the correct one will show up as the highlighted one, and the indirect one, if the connection is indirect, the regression coefficient corresponding to the recovered one will be low. So it turns out nicely that it is indeed the case. But I will tell you, this method has its limitations, and now we have a much better method based on multivariable ones. But this is the method that's already published, and therefore I'm happy to share this with you. So the conclusion is that y1 affects y2 directly. Why? Because this is the regression coefficient as a function of the library size corresponding to y2 hat given y1 hat given y2. Sorry about that. This is the regression coefficient corresponding to the contribution of y1 hat given y3. It says y1 hat given y3 is not needed when you have y1 hat given y2 as far as the recovery of y1 is concerned. So we put together and come up with this reconstructed causal network which matches with the true one. So I will conclude. A lot of points I've already mentioned, but what I want to say is that there are few new methods that have begun to appear, and there is tremendous scope for further research. And always remember, causal discovery is a challenging problem simply because there is no universal definition of causality, which is good. Each group specializes in one or two different forms of causality and contributes to the literature and to the resume. So thank you. The floor is open to questions. I would like to place on record all my due thanks to all the researchers. I don't have the list of names here, I'm sorry. But there are so many PhD students, master students, and few collaborators who have contributed to this research work that we have been doing in this field for the last 13 years. Thank you.
Thank you, Professor. Thank you, Professor Tangirala, for that very nice talk and starting from an historical overview about, and then going for case studies of using data-driven approaches. We have time for questions, so please go ahead and type the questions in the chat box and we can take it from there.
They can also go to reactions and raise their hand, and we can unmute them in that case. That's also possible.
Are there any questions in the chat window? It's like no. Somebody has messaged privately saying they have missed some part of the presentation. They wanted the PDF. That's okay. We'll share it later.
They have missed some slides?
Yeah, some of them have messaged me privately on the chat window.
Okay.
That they have missed some parts for whatever reason, and they wanted the PDF, but we'll make those